If your imagination runs wild with black holes, you're in for a scorching surprise. Picture this. You're drifting towards a black hole, and just as you think you're about to enter the point of no return, you hit an invisible wall of intense energy. So, what's a black hole firewall? It's a hypothetical barrier of high-energy particles right at the event horizon, the edge of the black hole. Some theories suggest this firewall could be the key to solving the paradoxes of black hole physics. According to quantum field theory and curved spacetime, each emission of Hawking radiation involves two mutually entangled particles. One particle escapes as Hawking radiation, while the other is swallowed by the black hole. Imagine this. A black hole formed a finite time ago and will eventually evaporate completely. During this process, it will emit a finite amount of information encoded within its Hawking radiation. But here's where it gets really interesting. For an old black hole past its halfway point of evaporation, quantum information theory suggests that new Hawking radiation must be entangled with the old Hawking radiation. This creates a paradox because of a principle called monogamy of entanglement. Essentially, a quantum system cannot be fully entangled with two independent systems at the same time. Yet in this scenario, the outgoing particle appears to be entangled with both the infalling particle and the past Hawking radiation. However, it is now accepted that the paradox assumed locality, a principle that may not hold true in quantum gravity theories. Some physicists believe that violations of locality can resolve this paradox, while others argue that such violations are insufficient. Some scientists suggest that the entanglement must somehow get immediately broken between the infalling particle and the outgoing particle. Breaking this entanglement would release large amounts of energy, thus creating a searing black hole firewall at the black hole event horizon. This resolution requires a violation of Einstein's equivalence principle, which states that free-falling is indistinguishable from floating in empty space. Imagine this: as you approach the event horizon of a black hole, instead of smoothly crossing a point of no return, you encounter a blazing wall of energy. This firewall would incinerate anything trying to pass through. This idea has been characterized as outrageous. Theoretical physicist Raphael has complained that a firewall simply can't appear in empty space any more than a brick wall can suddenly appear in an empty field and smack you in the face. However, the concept of a black hole firewall remains a hot topic in theoretical physics. Could it be that our current theories are incomplete, or is there a more profound truth waiting to be discovered, one that will unify quantum mechanics and general relativity? In the quest to resolve the black hole firewall paradox, many alternative theories and proposals have emerged. Some scientists suggest that there is, in fact, no entanglement between the emitted particle and previous Hawking radiation. This resolution would require accepting black hole information loss, controversial violation of unitarity. Others, such as Steve Giddings, propose modifying quantum field theory so that entanglement is gradually lost as the outgoing and infalling particles separate. This would result in a more gradual release of energy inside the black hole and consequently no firewall. The Papadodimas-Raju proposal posited that the interior of the black hole is described by the same degrees of freedom as the Hawking radiation. This resolves the monogamy paradox by identifying the two systems that the late Hawking radiation is entangled with. Since, in this proposal, these systems are the same, there is no contradiction with the monogamy of entanglement. Along similar lines, Juan Maldacena and Leonard Susskind suggested in the ER=EPR proposal that the outgoing and infalling particles are somehow connected by wormholes and therefore are not independent systems. The fuzzball picture resolves the dilemma by replacing the no-hair vacuum with a stringy quantum state, explicitly coupling any outgoing Hawking radiation with the formation history of the black hole. In January 2014, Stephen Hawking received widespread mainstream media coverage with an informal proposal to replace the event horizon of a black hole with an apparent horizon, where infalling matter is suspended and then released. However, some scientists have expressed confusion about what precisely is being proposed and how it would solve the paradox. The firewall would exist at the black hole's event horizon and would be invisible to observers outside the event horizon. Matter passing through the event horizon into the black hole would immediately be burned to a crisp by an arbitrarily hot, seething maelstrom of particles at the firewall. In a merger of two black holes, the characteristics of a firewall, if any, might leave a mark on the outgoing gravitational radiation as echoes when waves bounce in the vicinity of the fuzzy event horizon. The expected quantity of such echoes is theoretically unclear, as physicists don't currently have a good physical model of firewalls. In 2016, cosmologist Nyashev Shordy and others argued there were tentative signs of some such echo in the data from the first black hole merger detected by LIGO. These echoes could potentially serve as indirect evidence of a firewall's existence. However, more recent work has argued there is no statistically significant evidence for such echoes in the data. The quest for observational evidence continues as scientists seek more precise measurements and better models to unravel the mysteries of black holes. Will future observations uncover the elusive echoes of firewalls, or will they point us toward new, unforeseen phenomena? Imagine a spaceship, the Event Horizon Explorer, on a mission to approach a black hole. The crew, a team of seasoned astronauts and brilliant physicists, gathers in the control room, eyes fixed on the view screen displaying the ominous black void ahead. But what about the firewall theory? If it's true, what happens to us when we cross that threshold? If the firewall exists, we would encounter an intense wall of particles and radiation. Our ship and everything inside would be instantly vaporized. But remember, this is still a theoretical construct. We have no definitive proof yet. And what if the firewall doesn't exist? What happens then? In that case, we'd pass through the event horizon without immediate incident. The question then becomes, what happens as we move closer to the singularity? Would we experience spaghettification? Or could there be other unknown phenomena awaiting us? The crew falls silent, contemplating the vast unknown. The view screen shows the black hole's event horizon, a point of no return. To think that all our knowledge could be upended by what lies beyond that horizon. If firewalls do exist, they could reshape our understanding of quantum mechanics and relativity. Physicist 1, indeed. And if they don't, it raises even more questions. Could there be alternative explanations for the entanglement paradox and the information loss problem? As the spaceship edges closer, the tension builds. The crew's faces are a mix of awe and trepidation. Whatever happens, we're on the frontier of human knowledge. Our mission is to seek answers, even if they lead to more questions, and perhaps one day we'll find definitive evidence. Until then, we can only hypothesize and explore. As we continue to delve into the mysteries of black holes, we must ask ourselves, are we prepared to confront the unknown? Will future discoveries confirm the existence of firewalls, or will they reveal new, unforeseen phenomena?